Okay, so now I'm gonna find the Rthevenin, and I need to choose the test source method. It is a requirement of this class that you learn this. It's an outcome. And steps 1 and 2, I'm gonna do in one step only. I'm gonna turn off these two independent power supplies, and I'm gonna add a test source to that one. So here's my semi-dead possum circuit. 1K IA, and this is IA, and this is 2K. So I'm opening this current supply, and I will close the 4 volts, so it's only a 1K here. Bad drawing. And now there's 2K here, and I could either add a current source or a voltage source, and because there is a resistor there, I am interested in doing a source transformation, but later I will still have to come back and find this I here. So really the Rthevenin will be that 1 volt divided by this current I2. Let me call this I2. So in the end, I'm gonna do 1 over I2 to find that 1 volt. To find the current through the 1 volt. So it's the same as that one. So this is the new circuit we have. I can forget this original circuit because it doesn't have these two. I don't need to even worry about it. So I really need to find IA here, and I am tempted to do nodal analysis, but I just did nodal analysis in the previous circuit to find the Rthevenin. So instead I'm gonna do source transformation, and even though it's against my interests, so as soon as I do a source transformation here, you're gonna see I lose that I2. So, but it's a hit I'm gonna take just to find IA. So once I find IA, I'm gonna say that IA equals I1 plus I2. So here's my idea. If I find IA, I'm gonna find this voltage here. I'm gonna select this as ground. This is 1 volt. If I find IA, I'm gonna find this voltage here, Vx. If I find Vx, I'm going to also multiply IA by 1000 and find this Vz here. Once I find Vz, I'm going to say Vz minus 1 divided by 2K is I2. So in the end, I'm going to use Ohm's law. But really, this all depends on me finding IA. So I'm going to do IA here, and this, if you are a ninja with a source transformation, you're going to see that this is 0.5 milliamps, and this is 1K in parallel with the 2K, which is 2/3, which is 0.7K. And then I'm going to transform it back. So here, I hope you can still see it. IA is going down. 2K, 1K IA. .5 times 7 is 0.35 volts, and this is still 0.7K. Okay, so now I can use mesh analysis, or before we knew what mesh analysis was, we used this as KVL. And in this case, it's like this: minus 2K IA minus 1K IA minus 0.7K IA plus 0.35 volts equals 0. So this is KVL, which is minus 3.7K IA is minus 0.35. So IA will be 0.35 divided by 3.7 milliamps. So this is more or less 1/10 maybe, 0.1 milliamps. And now, once I find this, I'll go back to my original idea. So 0.1 milliamps means that Vx is 0.1 milli times 2K is 0.2 volts. Vz, supernode expression is Vz minus Vx is 1K times IA. So if you see here Vz minus Vx, and Vz will be 1K times IA will be 0.1 volts plus 0.2 volts. Vx is 0.3 volts. So if Vz is 0.3 volts, now I can use Ohm's law. Vz minus 1 divided by 2K is I2. So I2 will be minus 0.7 divided by 2K. Which I'm going to leave for now because I'm going to have to do 1 over that. So RTH will be 1 volt divided by I2, which is 2K. Actually, it's the absolute value of that. 2K divided by 0.7. Which is like 3 kilo ohms. So that's what I expect on the exam, for you to find the Rthevenin. It's very approximate, so chances are there won't be exact numbers, and chances are everybody's going to have different numbers. I'm more interested in seeing if you know how to use source transformation, KVL, ohms, supernode expression, you know, circuit resistors in series and in parallel. So there's all kinds of electric circuits concepts here for you to find the Rthevenin using a test source. I hope this helps, and you can use any other method actually. So this example here is just one way of solving the circuit, but there's many other ways that you have learned.